for the ramp up of these vaccines in about 14 to 18 weeks. There are about $20 billion worth of biological drugs and vaccines being made on our platforms today. So we are inventors of radial flow chromatography. Many of you may be familiar with them. We'll touch on them briefly today, and if somebody is interested in any of these things, you can contact us later. We have a whole line, very extensive line, going from the bench to large scale for chromatography systems and skids, single-use chromatography systems and skids. And what's become more topical and will be the subject of some of our talk today will be continuous chromatography, 2 and 3 column continuous chromatography, and the impact that's could potentially have on facility design and on capacity. Buffer management is a big issue in the industry today as you're scaling up. And so the ability to make these buffers in quantity very quickly on demand. And then, of course, facilities tend to have lots of hold steps, be very widespread, and cause a lot of capital expenses, quality control, etc. And so integration and intensification of processes has become very topical and what is today being dubbed as Pharma 4.0 or Biopharma 4.0, along with data handling and such. Okay. So, a little trouble going to the next slide. My computer, bear with me. Okay. So why should process engineers worry about facility design? I already said that. You know, it's a large capital investment. The smallest of plants may be $50 million, and of course, the large ones are over $1 billion. And the focus most often is on capacity, cost of goods, certainly regulatory issues, you know, in designing facilities so that you minimize bioburden. You have a workflow traffic. You don't want clean stuff going back into the dirty areas. Segregation, pre-viral inactivation, post-viral inactivation, and such. So quality issues, workflow issues, flexibility, that's becoming more and more important as companies are considering multi-product facilities. You know, used to be there was one giant stainless steel facility for making a blockbuster drug. Those are less and less common. And so the ability to make multiple products in the same facility, not at the same time, but, you know, in campaigns, is really very important. And titers and such volumes may be different for different drugs. So how do you accommodate all that? How do you remove bottlenecks? Adaptation of technology, whether it's software, whether it's automation, whether it's integration, online, at-line, and online process technologies. And then IT CSV, so IT is very much a part of that, integration of these systems with MES systems, computer system validations. Those are all issues that one considers developing when we're putting together a facility. Very often, some of the other factors trump process issues, and the engineering companies just provide sort of cookie cutter process factories, if you will, blueprints, and then the process guys have to make their product in those facilities. And there are limitations as a result of that. So I think this talk is really about, you know, how we can do much more to make facility designs more effective for our goals. And so the footprint of the plant on the process side, at least, you know, we're not talking about cafeterias and offices and labs and such, but consists of upstream media prep, filters, chromatography, buffer prep, UFDF, concentration, in-process QC, formulation, fill finish, right? Cleaning, storage, other tasks associated with the actual workflow. And then, of course, multi-product versus single product, single use versus multi-use, equipment, process flexibility, looking at smooth operation, lower FTEs. If you have lots of hold steps, lots of changes in the middle, your FTE, your headcount is going to go up. You have hold steps, of course, your plant footprint goes up, cost goes up, less tankage, less in process QC. So those are all the objectives that we have from a workflow standpoint. And of course, every plant objective is you maximize capacity per square foot. You can also put it in terms of capacity per dollar investment, capacity per FTE, and then eventually, amortize capital costs, flow into CapEx, and eventually into OpEx. But the OpEx consists not only of amortized CapEx, but FTEs, whether it's direct or indirect, utilities, maintenance, etc. And then the other factors like regulatory compliance and quality are usually very important. But I think more and more so, we are becoming cognizant of sustainability goals. Many companies have sustainability goals becoming more and more important. So whether you use a lot of plastic tubing and totes, waste, that all involves that has a net impact negatively on sustainability. I think we have to become more cognizant of. So traditional facilities here's an example of a traditional sort of batch-oriented facility where it's little tiny, but I'll just kind of point this out if you can see my cursor. But on the bottom part of it is the upstream from the seed train to the large bioreactor bays. And then as you turn the corner, the blue part is the downstream chromatography. Then you have buffer prep and column packing, etc. Column packing here, buffer prep here. You may have media prep on the other side and upstream, and you have the corridors lining this up, running up and down on the upstream and downstream side. So this is just an example of a facility. There are other models that just relates to the workflow of those particular processes. The bottom line is if titers go up, then the blue area that we are talking, the blue areas that are shown here, as you round the corner, get really impacted, right? So the columns get bigger, the skids get bigger, buffer tanks get bigger. And so if your facility is designed for a certain titer, it's great that the cell culture guys are now giving an output that is 5 times, 10 times that output in the same space. But downstream doesn't work like that, right? So the more protein you have, the bigger facilities you need. And usually these are the areas, stress points in the facility. So to counter that, people may be doing more cycles, or trying to fit bigger columns in, or you go to facilities where there are totes, lined up all along the corridor. People are stopping processes and moving totes back into the clean rooms and pulling them out. And so it's a real mess. And then as titers go up, this is another example of facility, and the question and the terms that are often used are form, fit, and function, right? So you have a form for a certain facility and designed to fit a certain process, and the function is an output of that. As really, the question is that in terms of the design, it's backwards, right? We should look at the function first and how that's all going to fit, and then what form is the facility going to take. So, the thinking generally is backwards, and then we build these constraints into facilities. And as titers go up, you can see in this model here, we've decluttered it. So, so you can see that a huge amount of space is allocated to buffer prep and buffer hold Okay, so you're talking about, and if these buffers are in totes or tanks, because people are moving away from stainless to plastic totes now, a huge amount of totes, and moving them around, stacking them, connecting them just requires a lot of labor. And there's QC involved with these things. So, and we are not talking about office space. This is premium space. So it's thousands of dollars a square foot, clean room, class 7, ISO 7 type space, or maybe ISO 5, depending on where you are in the process. So what limitations do process equipment choices place on facility design, footprint, workflow, and capacity? And so, we wrestle with this. And I think those are the areas of both problems and opportunities for us who are dealing with downstream processing, and really relate to the conundrums in chromatography scale-up. So as you scale up conventional downstream processes and you're going to higher and higher titers, what's going to happen, right? Your bioreactor, instead of doing, a gram a liter, now does 5 grams a liter. You've got 5 times in that 1,000-liter bioreactor, or 2,000-liter bioreactor. Instead of making kilogram of product, you're making 5 or 10 kilograms. Well, the current columns that you have aren't going to work. The current skids are not going to work unless you're doing 10 times as many cycles, right? Then your campaign time is going to be extended by 10 times. And you can have more shifts, but your buffer capacity has to go up by 10 times. So it's not just one isolated thing that you flick a switch and make a bigger column and you're done. So bigger columns, bigger chrome skids, more chrome skids, more cycles. And by the way, I'm talking chrome, but this applies to other downstream equipment, whether it's TFF or UFF, UFDF, right? So longer campaigns. We're doing more cycles to deal with the higher titers, longer campaigns. And what does that mean? It means more headcount, right? More QC, you're doing more batches, more documentation, more training. And it stresses the infrastructure, right? Because if your liquid handling, your water handling systems, your air handling systems, et cetera, are all stressed as a result of this higher level of activity. Of course, QC labs. So all this means more time and more money. So, I mean, we in the industry say, oh, it's so great, we are going to higher titers, but I think, and that is great, but downstream, we have to be able to deal with that. And facility-wise, in terms of workflow-wise, equipment-wise, process-wise, and facility-wise. So those are the direct consequences on the chrome or downstream part. But then support-wise, increase in buffer making capacity. We need bigger square footage, more gray space support, more complex work schedules, production planning, multiple shifts. So these are, and so, we'll start, and so it's a complex problem, and the simplest way to deal with complex problem is to break it down into bits and deal with where is the low-hanging fruit? What can we do on the process side as process engineers to really put the best tools forward so that we can be anticipatory of these kinds of problems and put in the right technology in place from the get-go, so we're not going to be encountering these problems, or we'll certainly mitigate them, right? So larger columns, conventional columns are slow. They have long cycle times, pressure issues, large space requirements. So, if you've designed a 45 centimeter column, 30 centimeter column, it's no big deal. But if you're getting stressed and you have to go to 2-meter columns, there's a whole packing around it, there's infrastructure, how to pack these columns, there's infrastructure, there's flow rate issues. So those need to be thought through, and they impact the plant design. Conventional chromatography systems, if you're running a batch process, fine. Again, you go to bigger systems. Well, there are certain standard systems that are available in the market. So now you're all of a sudden going into customized large systems. which is fine, but then lead time becomes an issue, supply chain becomes an issue. And then, you have more and more buffers. So whether you're going to single use or you're going to large tanks, if it's stainless steel tanks, you're invariably cutting down, tearing down walls and putting bigger tanks. And if you have single use, you have more and more totes, and you need space for those things, and you need people to handle them. Especially if you have batch processing with intermediate steps, right? So, of course, columns, we are all familiar with conventional columns and pressure issues and scalability issues with those. What works in a small scale isn't, you can do little, runs on high trap columns. They work fine with ion exchange. But when you go to large meter columns, they're 20-centimeter bed heights. Why? Because packing large columns, having large diameter columns is a problem. And we all of a sudden slow down our flow rates and deal with higher back pressures. So anyways, those are problems that we deal with. So how can Sepragen help solve these problems? Well, we have a variety of tools in our tool chest that address these issues. And quite dramatically, it's not minimal effect like 10%, 20%. I mean, you could have like just putting radial flow columns in, you reduce the footprint by 50%, and your cycle time as much as 400%. So just a hardware change on a column can impact that. And no longer, and these technologies are so well established that no longer are these changes being made where somebody says, 10 years ago, yes, you're trying something new. Oh, my PD guys have to use this column, and then we scale up from there. These columns have been used in change via simple change control, and phase 2 clinicals, phase 3 clinicals, and now post-approval changes. We are, for instance, doing one of the largest insulin plant in Asia with these columns, a 5-ton plant, right? And that's an approved drug for many, many years. So, and that's for insulin. So, it's a very common, very simple way. Contact us, we can work with you. Another a game changer really that's coming up is the use of continuous chromatography. There are conferences on it, people are going to it, but it's really not the domain of the elite now or few innovators in this space. The technology is proven, and the size of the plant can be reduced dramatically. So certainly, I'm on the technical advisory board of NIMBLE, which is an institute designed for innovation and biomanufacturing, and they're looking at. You can contact them if you're not a member, become a member of them. At next generation technologies, and certainly continuous chromatography is one of those that's going to dramatically impact our ability to produce large amount of biologics at lower cost in smaller facilities. And we'll address that here. So reducing FTEs, reducing intermediate hold tanks, reducing column sizes, right, dramatically, right? And then what we're also going to talk about is as you put a new technology in, it has impact in other areas. So when you go to continuous processing, so instead of doing, one big batch every week, in chromatography, you're running chromatography continuously. So you might be doing like the equivalent of 9 or 10 cycles, a day, and with multiple columns running at the same time. So your columns can be smaller, the facilities can be smaller, but you're now producing huge amounts of buffer. So in some designs, you'll see that the buffer making and storage component of the plant goes up dramatically, right? So how do you handle that? Well, what we've developed are systems, very unique, and the first ones in the industry to have, or first ones in the world, to have continuous chromatography systems with built-in or inline buffer blending. So you don't have any intermediate tanks. You just go about doing your chromatography. And from stock concentrates, the buffers are made in line. So the equilibration buffer is made, the wash buffer is made, the elution buffer, you're eluting at the same time, you're loading at the same time. So it really compresses the footprint. And then the other thing is process integration. We've got currently a mindset of you do one chromatography batch step over here with a anion exchange, or you do a hydrophobic interaction there, then you do nanofiltration somewhere else. And I think we are looking at more and more process intensification. So how can you integrate these unit operations into single skids so that you can do multiple things all at the same time, coupled with buffer blending, so you can shrink down the downstream proportion of your plant. So we'll address that very quickly as we go through. So this is for the uninitiated who don't know about radial flow columns. These are radial flow columns. The scale up in these columns is vertical, so the flow comes in instead of going axial down the axis of the column. The flow is applied to the entire outside wall of the column and travels radially in and out the bottom. So the bed height is now the radial distance or the annular distance between the outside and the inside of the column. And the column is just scaled up vertically. So as you scale up from one scale to the next, so you double the scale, you can flow twice as fast, you can load twice as much, but your back pressure remains the same. The flow rate is now doubled, the elution time remains the same, and the footprint remains the same, right? So you can see, and these things have been proven time and again, and all kinds of absorptive, desorptive applications, whether it's ion exchange, affinity, and so forth. And you can use the same resins that you're using in your current process, whatever media, whatever make, etc. And so this is how these columns work. Gives you a quick snapshot of that. And somebody has questions, I can answer them towards the end. But essentially, instead of having circular frits on the top and the bottom, the flow is applied to the entire outside wall of the column and travels through what is the outside cylindrical porous frit, radially inwards. And there's another frit, concentric frit in the center, inside which is a solid core. So the resin is held between these two concentric frits. The flow is applied to the outside, travels radially in through the packed bed and out the bottom. So you have a very large area over which you're applying your flow. So the flow rates are much higher than conventional columns, and the back pressure is very small. And there's data from third parties that have been presented at conferences, etc., showing, for instance, here that with axial flow, a process that was taking 8 hours with the radial flow could be done in 2 hours. And as far as product recovery, monomer HCP, DNA, lease protein A, all the release criteria for that particular batch was the same, right? So it's a low-hanging fruit. You can simply reduce the cycle time by as much as a factor of 4. By changing your hardware, you don't have to go to a faster resin, change anything in your CMC application, anything like that. So very quick, very fast. And we worked with several companies on these, and we can support you should you desire to go down this route and discuss with us. Now, continuous manufacturing. So Sepragen developed a QuantaCep CCS fusion continuous bioprocess system. And continuous systems, we are not inventors of continuous chromatography. It's been around for a while, but we are applying it in a way where it's suited for large-scale bioprocessing, both small scale and large scale. And and single use. Now, what's the directive for this? Well, in 2013, Janet Woodcock, who was the FDA director, right? When she was before the Congress, she was challenged to, to look at reducing costs, increasing our manufacturability capability, process robustness. And, she stated that, one of the ways that the industry or drivers making these changes would be to move to a continuous manufacturing platforms. And in 2017, CETA finalized the guidance on going into continuous manufacturing. right? And the guidelines are there. So certainly you have regulatory impetus. You're not fighting the tide. The regulatory impetus is to move towards continuous processing. And the FDA supports that. And the way we do chromatography, we take a lot of your batch data from conventional chromatography, for instance, and can be directly applied. Those methods that you made can be directly applied into continuous processing. So the transition is seamless. The regulatory bodies support that. Used to be people would say, oh, well, how is a batch defined? Well, and the answer to that was done years ago, because in cell culture, you've got product being made, many drugs being made in continuous perfusion, and you decide the level of the pool. And, on the cell lines, if you've got stable cell lines through so many different generations, then you've got the data to prove that, and you can go ahead and pool that data and consider it for release. No difference here in downstream processing. So if you want to scale up, this is just pictorial. It's not our data. This is just lifted off of a paper in the industry put together by John Kaufman. So other people have been working in the area of continuous processing, and they have done a lot of good work. You're welcome to look at those papers that are published, where they've talked about what it takes to scale up conventional processes, what the impacts are as you scale up these processes. And then if you go to continuous processing, then the footprint of the plant can be, we showed you the footprint of those plants. The footprints of the plants can be reduced considerably. And one of the strategies is to use inline, what is known as buffer making, or in the parlance of a particular vendor, it's called inline conditioning, where you have stock concentrates, whether it's acid or base, concentrates of buffers along with water and salt. And then you can use these machines with inline mixing to create different buffers. And the idea in this kind of facility design is you use such machines to create concentrates, and then you have holding areas for 3 or 5x concentrates. And then these concentrates can then, which are in, let's say, 300-liter tote bags, and then these can be then connected to chrome skids, where you can do your multiple steps of unit operations. So doing so certainly reduces the area significantly, but then it still creates about a third of the facility holding area for buffers. And for people who are not familiar with continuous processing, you often have, in its simplest form, while one column is loading, the other column is going through the elution, right? Going through elution, regen, and equilibration. And the first column goes to load, which is what is shown here. In normal columns, you have load phase, you have elution, you have load, stating very simplistically. So while one column is loading, there's no production that's going on. There's no output, right? The output is only when you're eluting. So if you have two columns, then you have continuous output, because while one column is loading, the other is eluting, and so forth. Right? So one is loading, the other is eluting. Or one is eluting, the other is loading. This is loading, that's eluting. And then some folks have gone to 3 columns, where they maximize the load capacity of the first column, because you have a sigmoidal absorption curve, and so you can load till the end of that sigmoidal absorption curve. Not necessarily useful in all instances. There are other ways of doing it, but certainly some people have adopted that, or you can have even more columns than that. But that's the idea in making the process continuous, is that you have a continuous output, and then going then into the next unit operation, which is then going into the next unit operation. So your entire plant is working, all the phases of your plant, all the unit operations from cell culture all the way to the end are working constantly. And again, from the same paper that I just referenced, they have taken a bunch of processes, continuous process studies that were done, and they have shown the impact of continuous processing on various factors, right? Whether it's productivity increases, anywhere from 4 times to 11 times, resin capacity increases, buffer reduction, etc. Right? So more and more data will come up. Different people will have their processes arranged differently. But one thing is constant, that the productivity increase is not in percentages. It is, anywhere from 4 to 10 times, right? And you can, depending on whether it's 2 columns or 3 columns or how you handle that, the resin capacity increases, potentially reduction in buffer usage. And so all this leads to a shrinking down of the facility size, which is shown in the first column, could be an average of 50% reduction in facility size. And complexity, because you're eliminating. So you have smaller facilities, less buffers in continuous production. Here's another article, and so which was very well visually, diagrammatically represented it here, where you have batch production on the right and you have continuous production on the left, showing what the impact is. The plant size actually is even smaller.
Pulse is 63 per minute. Your systolic value is...
Can you please mute whoever that is? I'm sorry. So since the entire process is running, your columns can be reduced by as much as 10x. Your daily buffer consumption is much lower. You don't have intermediate surge and hold tanks. And you don't have to deal with QCing and hold tanks. And certainly labor associated with moving these things around. I mean, I was at one of these facilities where we had a young engineer from a well-respected school, and he was telling me, he said, well, now I know why I did my PhD, because I can be here in the production room moving all these totes around and making connections all day, as opposed to, and stopping and starting processes, as opposed to, doing the stuff that I was really trained to do. But I think it really shows, I say that a little tongue, I think he meant that a little tongue in cheek, but I think it states to where there are inefficiencies in the process and how we can make these processes more efficient, right? And it means that getting high quality people is tough in this industry. And so, if we can utilize those talents more effectively and not have to, and reduce FTEs, of course, at the end, it reduces our costs, but I think it makes for greater job satisfaction. You don't have all these totes you're dealing with, and it's greater for sustainability. So all this requires more footprint, extra tanks, QC, more people, etc. And so Sepragen's developed these systems, which are multi-column continuous systems, but we've integrated these with inline both buffer dilution and buffer blending capabilities. I mean, if you're doing a process continuously, then you're continuously using buffers. And to make buffers in batch, put them in totes and drag them around, you're just transferring one bottleneck to another, which is what is happening in many of these facilities, and which really is stopping the adoption, I believe, for moving to continuous processing. So the facility footprint is a lot simpler, a lot smaller. You make your stock, you just have a room where you're making stock concentrates. So you have the acid and base component of your buffer. If you have additives like sucrose or something, you have those in concentrated form, 3 molar salt, And then those, can now be, if you've got 300-liter totes, and each of these constituents are, at those high concentrations, and you have Wi-Fi coming into the room, then the buffers are made in line on demand, and really behind the scenes, the operator is just running the equilibration step. That's it. Buffers being made. Don't have to worry about it. And that monitors pH, conductivity, that monitor the quality of the buffers that are going in. As part of the IQOQ, we provide the ability to validate all that, right? And then you have your upstream, your downstream, your post-viral purification. That's it. Very simple facility. The footprint is much reduced. You don't have a lot of intermediate tank storage areas, reduced labor and reduced cost. And these are not systems we have done this on a bench scale, meaning we have systems that are, 5-6 liters an hour up to, thousands of liters an hour that are running manufacturing. And we've done this in multi-use as well as single-use systems. So if somebody wants to run a multi-use, multi-process or multi-product facility, they simply change out the entire tubing path, which comes pre-sterilized, put another one in, and you can start the campaign for the next month or two and run a different product. Right? I think, and then the other thing that, so here's a complete antibody process where it's a simple model to take. Other people may have different proteins, but since it's so widely published and everyone knows the steps involved, it's simple to model and talk about. And so here you have the first step is the capture skid, right? Then you go through viral inactivation, and then you go through AEX, potentially CEX, or AEX, hydrophobic interaction, and nanofiltration. So of course, a lot of focus has been there. Adam's asked a question. Adam, I'll address that in just a minute, but let me just finish up with this. So most people, when they talk about multi-column or continuous chromatography, the focus is really on that first step, which is an absorption step, and and reduction of use of protein A, where you have multiple columns, and you're eluting the antibody. Then you go to a hold tank, and you have an acid hold. Somebody may want to use, I don't know, some other methods for viral inactivation, but the low pH hold is a very simple one. And then the pH is then neutralized, and that then the material, the harvest or the purified antibody is pumped through filter, through the anion exchange column. The buffer is adjusted to high salt, run through hydrophobic chromatography, and then through a nanofilter. Okay, so these are all individual steps with whole steps in the middle currently, right? And they are run at different times. Now, what we have done is we've created, and this is in manufacturing scale, right? So we'll show you pictures of these. Obviously, it's been done on the labs on small scales. So where you have these multi-components or the concentrates, you've got column flow direction, you've got buffer distribution, and you've got fraction outputs coming out. So harvest is going onto the column continuously, and the buffers are the individual buffers from stock concentrates are being made in line, all simultaneously, right? And it's a multi-column capture. So, and then we've integrated these with viral inactivation. So here's a PNID of that. You've got the harvest. going into one of the two columns, and then you've got, your buffer pumps. So this is a screenshot of the user interface, and the buffers are being made by the Wi-Fi pump and the concentrate pumps and directed to one or the other columns. So we've done multi-columns, we've done two columns, lots of flexibility in how we've designed these kinds of systems. And then here's a 3-column system. We are loading onto one column. See, the orange is the load. You load onto one column, goes through the first column, goes through the second column. And then the buffers are being made simultaneously, and they're going on to the third column that is preloaded. And just in the course of doing that, we may have like a 200 odd millisiemens stock solution, and there's an equilibration buffer being made at 10 millisiemens, a wash buffer being made at 45 millisiemens, and simultaneously the pH is also adjusted to whatever their value is, right? So yeah, so it's these are not buffer dilution systems. I want to stress that fact. These are stock concentrates, right? So you may have an acid component of a phosphate buffer, so monophosphate and monobasic phosphate or dibasic phosphate. And then you may have 3 molar salt and water, right? So the monobasic might be 1 molar. So if you say, okay, I want a 0.05 molar phosphate, and I want at this pH, whatever it is, 6.5, 6.8, 7.2, then the stock concentrates are gonna, the acid and base components are gonna mix in a certain ratio with the water to give the pH, and the salt will marry with that stream, and provide the right level of conductivity so that what's coming out is not only the right molarity, but the right conductivity and pH. And it's delivered in real time online, which is very different from like you make a concentrated phosphate buffer, right? So you still have to mix the acid and base component, and instead of making a 0.05 molar phosphate, you might make a 0.5 molar phosphate and dilute it by a factor of 10. So you're not doing that. So from the same components, different buffers with different concentrations and different salinities are being made on demand, right? And so, yeah, you don't have to have people moving totes around or, anything like that. You're not having to make concentrated buffers and dilute them online. Other people make Chrome systems, and you can dilute, to do a 5x, 10x dilution. And we do that as well, but we are talking about actually generating. And you can have different buffer components. You've got three inlets on each of the pumps. So you could have an acetate buffer as well. You could have a citrate buffer. You could have a tris or phosphate buffer being made in different steps, right? So, and yes, these are being used in large scale, Adam, to answer your question. We don't simply make these toys for people so that we can show people. You're looking at machines that are doing 600 or 1200 liters per hour that are connected to, large scale perfusion systems. So this is serious. We have bench scale versions of these machines, smaller scale. I wouldn't say bench scale, but smaller scale, under a liter a minute, for people doing, scaling up such a process. But for people who, shown enough flexibility, we have designed these systems, and we have completed FATs, right? And we have shipped these systems, including all the GMP stuff that goes with it, the software being 21 CFR Part 11 compliant, working with our clients, CSV IT teams, interfacing through OPC UA for data loads, for login authentication, So many things that go into large scale production. And as far as drift and all that is concerned, we have process alarms. So we give a band, right? And you can see the conductivity and how stable it is. You're starting with stock solutions that are over 200 millisiemens. And what you see here is about 10 millisiemens, right? And that is achieved within a minute. pH takes a little bit longer, maybe a minute and a half, but we are running in seconds here. But again, very stable. And you give a bandwidth, so it might be 5 millisiemens, or it might be 0.1, 0.2 pH units, 0.2 pH units. So if it's outside of that, it gives you a process alarm. The buffer can get ejected out. So I know we are nearing the end here of our talk, and there might be questions, so I'm going to go through it a little quickly. And this is a bench scale, smaller scale system. We have a single use continuous three column system, which goes up to 300 mils a minute. It has exchangeable flow paths, so you can use a 1.6 millimeter single use flow path and go between 0 and 100 mils a minute. If you're developing a process, or you can go up to 300 mils a minute. Similarly, we have a 1 liter a minute single use flow path continuous system and a 3 liter a minute. And you can look at all the UV conductivity, pH trends, switch buffers based on time, volume, UV. We can even do gradients in these systems. So complete documentation, event log, alarm logs, all that. So yeah, here on the left-hand side, you see the bench scale single-use systems, right, with removable flow path. And then you have the 2 column systems in the center. And with all these buffer blending and buffer dilution are standard. We have lots of standard chrome systems going up to 125 liters per minute. And those are all capable of doing inline dilutions. And then this is another single use continuous multi-column system with inline buffer blending for large scale use, obviously. And just the buffer blending capability of it, there's a test case, particularly during the time of the COVID crisis. We were asked by a company to, so of course, we were asked by a company to help them scale up their COVID vaccine production from 40 million to 200 million doses a month and do this in about 3 months. And they wanted 7,500 liter an hour system. So 125 liters a minute. They didn't have the tanks to make the buffers. They wanted to use the existing facility because it was surge capacity. And this video just kind of shows you, I don't know if the audio is actually hooked up, but this just shows you, I don't think I connected the audio on this. Sorry. But anyways, let's see if we can get the audio. May have to stop share and come back again. Give me a second. Okay, I think I'm gonna just go back to where we were. The bottom line is that, and if somebody is interested, we can send you this video, but it shows a 125 liter a minute system that we put together in 14 weeks for this company. And because they didn't have the tanks to make those quantities of buffer, they were running 24/7. We had these 5 pumps and buffer concentrates and individual concentrated solutions were all put together, and these kits were shipped out in in 14 weeks. So they could use the existing small tanks that they had to have stock constituents, and the buffers were made in line. Okay, so, and something about the design of these skids, but again, different concentrations of buffer from different stock solution concentrates that they had made. You know, if they had a 200 million salt, or even if they had 150 millions of Siemens salt solution, it didn't matter. The buffers were delivered to the right pH and conductivity to the columns, right? So regardless of whether the input was correct or not, the system still performed. And so we've done these installations around the world for our columns, our equipment, our systems, and on customize and a lot of customization. So we're not arrogant enough to say that, you know, we've designed something and, you know, you either get this model or not. We realize that in manufacturing, each plant is different, systems are different. There's a lot of handshaking and software that's required. So our software is customized, and we have a large PLC and software team, and we interact very frequently with different users on their platforms to ensure that this is done. And our process is very detailed. We start with, you know, our customer's URS, and we go to the FDS. After that, we go through P&ID reviews, we go through GA drawings, and then we go through an entire DQ process, which looks at all the risk factors. There's risk analysis associated with it, and then what we are going to do to mitigate those risks, right? And there's a software design review, there's a hardware design review, and then implementation, of course, FAT, SAT, IOQ, and then the whole turnover package that comes with these kinds of machines. And very often, if somebody's got like explosion-proof systems or something like that, or certain CE approvals, other things that they need, then, you know, we've designed for those as well. So lots of customization. We have a project team that runs that. I mean, we are not great marketing guys, but we are real world-class geeky engineers here. So lots of different companies that we worked with over time. So proven technology, high performance, and nimble organization. So somebody is asking about how often do pH need to be calibrated? Usually at the start of a campaign. And we have single use. We make our own pH sensors, our own conductivity sensors, our own transmitters. We do all the manufacturing in-house, 3D print a lot of parts. So I'm going to stop sharing, and if you have questions, happy to answer them. We have a few minutes left. And the way, of course, these systems help reduce footprint is quite obvious, that you don't have to have that huge space for making buffers or even buffer concentrates, right? Yeah. So somebody may say, okay, I'm going to make a 3x or 5x concentrate. Well, you still have to store those concentrates. It's better than not having any concentrates, but you still have to store those. You still have to manage them. You still have to QC them. You still have to move them to the chrome skid. We have to move them out. We have to put other ones in, or you have to have surge tanks in the middle with level controllers and pH controllers. So all that is eliminated. Lots of labor, lots of time, and it's a reality. I mean, this is something that we've done. It's not conceptual. This is going into actual manufacturing of GMP product. Yeah. And so we did show you, what the slides were. It's a very simplistic slide for reducing the footprint of the plant. I think somebody asked that question, so let me go back, see if I can pull that slide up and go out of this mode. I think it's going to be a little difficult to go back, but we can certainly get back to you guys on this. Yeah. Any other questions I can answer? We can unmute Sanjeev if they have a question. I can take it right now.
I don't see any more questions.
Okay, well, thank you all very much for joining us today. You're welcome to reach out to us privately if you have questions. We can do a one-on-one, go through this in a little more detail and answer questions pertaining to what your specific needs might be or your thoughts, or if we triggered any ideas that you want to run by us. Love those situations. We'd love to brainstorm with you and see what kind of an impact we could have on, your cost, your facility, and what if you have bottlenecks, how those could be alleviated. We work with a lot of companies and a growing number of companies now, so absolutely would be delighted to have a talk with you. And thank you for joining us today. Have a great day.